Everyone, it's Aniruth from 61BL. Today we're going to be talking about the final, specifically a question on graph algorithms. So we're going to start with part A. We have some graph here, A, B, C, D, E, F. And we're trying to find first the shortest paths tree using Dijkstra's by running it on vertex A. And then we want to find the ordering that the vertices are visited in and what edges are included in it. So we can go ahead and get started. So with Dijkstra's, we want to sort of maintain a queue. And then as we add vertices, we're going to use our queue to sort of rank them by the distance away from A. And that way we visit the nodes that are closest to A. And as we visit nodes, we update the surrounding nodes distance. So I'm actually going to go ahead and just draw this on the graph. You could also draw this on a separate table, but I find that it's easiest for me to go ahead and keep track of everything on the graph itself. So we start with A. To show that we've popped A off, I'm going to go ahead and draw a little red mark on it. And when we pop off A, that means that we're going to go ahead and update B and C's distance, because before we thought they were unreachable, but now we know that B is reachable by a distance of 1 and that C is reachable by a distance of 2. And then we're going to pick the smallest, right? D, E, and F have like infinity or can't reach values. So out of all of these 5 remaining vertices, B has the smallest distance away from A. So we're going to go ahead and pop off B from the queue. When we pop off B, that means that we can go ahead and we know we're going to be using this edge AB no matter what. And then we can go ahead and update D and E distance as well. So if it takes 1 to get to B, that means that we know that it could take 3 to get to E, and that could also take 2 to get to D. And now we're put in a bit of a conundrum. We need to tie break between C and D because both C and D both have distance of 2, but we're told to break ties alphabetically. That means that we're going to go ahead with C. So I can go ahead and then visit C. As I'm visiting it, I know that I'm also going to be using the edge AC, so I can go ahead and underline that. And then I can go ahead and also update any values. So the distance to E using AC is going to be 5. That's not better than what we currently have, so I'm not going to update it. And then we can also find a new way to F. So I could use this distance of 2 plus the distance of 4 to get F as a distance of 6. And then I look at D, E, and F. So then I'm going to go ahead and visit D because it's only a distance of 2 away. So I go ahead and mark it. And in doing so, I confirm that I'm going to be using BD. And then I don't update ABE. Even though it's the same distance, I only update it if the new way is shorter. Otherwise, why update is sort of the reasoning. Because it'll take time to sort of rearrange the priority queue if needed. So then that means that we're going to go ahead and mark this, but then we're going to look at E and F, realize that, hey, E has a distance of 3 from A, which is shorter than F. So I'm going to go ahead and visit E next. And the way that I get to E would be by using BE. And then I'm going to go ahead and finally update F, because we were going to use 6, but now we realize that there's a shorter way by going around. So we realize that if we can get to E in distance of 3 and it's just 1 more to get to F, then we can actually visit F as a distance of 4 away from A. So now we've sort of figured out what order and what way we'll be going ahead and visiting them. So it turns out that for this particular question, I didn't track this as we were going along, but we actually are just visiting in the same order that the example is, just in alphabetical order. And then in terms of what edges are rooted in the SVT rooted, what edges are included in the SVT rooted at A, well, that's just everything that we went ahead and underlined. So we should, if we have 1, 2, 3, 4, 5, 6 vertices, we should have 5 edges. And in this case, we have 1, 2, 3, 4, 5 edges underlined. So I'll go ahead and mark them. We have both the edges from A We also have the edge BD and BE. And then we also have the edge EF. Those are our 5 vertices. Next, we want to run A star from A to F on the same graph. So as you can see, I've sort of replicated on the right-hand side here, so we can draw on a fresh graph. And we want this time to have a heuristic as the number of edges between B and F in the BFS tree. So I've gone ahead and already written it out. We know F, well, we start with F, right? So it's going to have a distance of 0 from itself, according to the heuristic. And then we have C and E. So with C, we know that C and E are both 1 level away from F. We know that A and D are also a second level if C and E are 1 level away. And B, since it's connected directly to E, is also on this second level. If this connection BE was not there, then B would be a 3rd level connection because it would only be connected to A and D, which are both 2nd level connections. So now we're going to be running A star. So A star is very, very similar to Dijkstra's, but the difference is now instead of just having the distance from A include the distance from the start node A to the actual node itself, we're now going to be adding that, right? So the edge weights that we were using previously with the heuristic as we go along. So now let's go ahead and get started. So we want to run A star from vertex A to F, which means that we're going to be stopping as soon as we visit F. So in terms of what order we visit in, let's go ahead and get started. We're going to go ahead and start with A, just like last time. And then we're going to go ahead and update B and C, but this time we're going to be adding in the heuristic. So now when we update B, 1 plus 2 is going to be 3. And then C, 2 plus 1 is going to also be 3. So this time we're going to have to use the same tie-breaking logic and go with B instead of C because B comes alphabetically prior. So then we're going to go ahead and pop off B. And then we also need to go ahead and then update D and E. So if I go ahead and update D and E, then if B had a distance, well, we would originally have that A to B is 1 and then B to D is 2. And then since D has a heuristic of 2 more, that means that I would go ahead and have a total of 4. And then to E, right, according to AB, then BE, I would be using B has a distance of 8, right, according to just this edge weight, and then we factor in the heuristic at the end. We'd have 1 plus 2, 3, right, as we did here before, E would be 3. And then we add in the heuristic of 1, so we realize that it's actually 4 away, according to this whole process. And then, so this is how we've set this up, and then we are going to go ahead and visit C, because C's 3 is less than E and D. So we go ahead and visit C, and you make any updates. So let's go ahead and check if we can update E. Well, we can't because the heuristic of E is going to be the same. And it's going to be very similar logic, right? Going along this way is 5 plus the heuristic instead of going the current way that we've already found, which is 3 plus the heuristic, right? So we've already identified that. And then we want to check, okay, well, do we also need to update the value for F? So we have 2 plus 4 is 6. 6, well, that would just be it. So you have 6 for F. And then when it comes to visiting the rest of them, we're going to go ahead and then visit. Oh, I forgot to underline all of them, but I can go ahead and quickly do that. So we visited those 2. And then we're going to go ahead and visit D because it has the minimum weight, but then between D and E, D comes first alphabetically. So I can go ahead and also underline to confirm that we're going to be using B and BD. And then we have to check how we can get to F. So when I visit D, I think, okay, well, I could go 1, 2, 3, and then E I could put as 4. Well, I don't really need to update that. So I'm going to go ahead and then just continue using E as before. So go ahead and mark it. I will mark this too. And then finally, I will realize there's actually a shorter way to get to F because when I visit E, this is when I can update using the edge EF. So then I'm actually going to go ahead and mark that we are going to use EF, update F to be the value 4, because now we're going to use AB, BE, and EF And then we can also pop F off, which concludes the whole process. So something that's like pretty important here is, and I'll go ahead and use this red, is we're going to be following A to B like this. Then we're going to be following B to E, and then we're going to be following E to F. Because with A star, even though we're exploring all these other nodes, what really matters is that in terms of the shortest paths from A to F, we just want the edges that are going to comprise that. So I'll go ahead and actually sort of counteract it and go, what edges comprise the shortest path? I'm going to go ahead and pick AB, right? That's the first one. Then I'm going to pick BE, and then finally EF. So I don't pick all the others. I'm just looking for one path. But in terms of the ordering that the vertices are visited in, it turns out, based on what we just did, it's actually going to be the exact same as the previous one. Even though we had a heuristic, then it changed some of the values and some of the considerations, but it still looked to be the exact same as the example actually that was given. So now we're going to be running prims from vertex A. Well, I have it recopied down here, and I can go ahead and write prims just to remind us that we're using prims. And now you want to find the ordering that the vertices are visited in. Format your answers as a space-separated list. Okay. Well, the nice thing about running prims is that prims is very much like Dijkstra, except the difference is we no longer think about distance up to, we just now think about edge weights. So we're starting with A. We can go ahead and do a very similar process. I can go ahead and pop A off the priority queue. And then I can realize, hey, well, B is a distance of 1 away from A, C is a distance of 2 away from A. So I can go ahead and mark B with a 1 and C with a 2. But again, that's not really what I'm doing. I know I said distance 2. We mark it as a distance 2, even though it's just the edge weight. But that'll make, like, I think, a little more sense when I go to the others and I don't add. So we have this, and then I'm going to go ahead and visit B, because B has the next smallest value of 1, right, compared to C's 2. So then I go ahead and I visit B, and then I make all the updates as needed. So next, I will go ahead and update E to realize that E is going to be 2, and that D is going to be 1. And then I look at the 3 options that I have, C, E, and D. Again, F, we don't really know how to get there, so that's like some undefined infinite value. So then I go ahead and I visit D because it's the next closest, right? Or next smallest value. So along this way, I've used A, B, and BD. Next, I'm going to go ahead and see if there's anything to update. Well, I don't have anything to update. And then I will go ahead and determine whether I visit oh, sorry. There is actually something to update. We're going to be updating E to 1. And then we'll go ahead and pop E off. And then we're also going to realize that when we pop E off, right, E we popped off before C because it has a value of 1, that we can actually get to F in 1 as well from E, right? So that means that this edge weight is 1, so we're going to mark it as having 1. And then we're also then going to go ahead and pop off F. And then finally, we're going to come back and pop off C. When you look at how we did this, we really are just going for the least weighted edges. We picked all the 1s, and then we picked this 2. We didn't, well, I guess like one way to think about it, I guess this is more like a Kruskal's way of thinking about it. We didn't pick this BE edge, right? Because we already had a BD and DE edge. But we picked the AC edge because it was better than going with the 3 or the 4 options that we had. So the ordering that the vertices are visited in is we basically went around, right? A, B, D, E, F, and then finally we came back to C. And now we need to look at what edges are included in the MST rooted at A. Well, it would just be the edges that I have underlined. So it's going to be, again, A, B, A, C, and then we're going to include BD, but we're not going to include BE. Instead, we're going to include DE. We're also going to be including EF. So these are our 5 included, right? Because if we have 6 vertices, we need 5 to make a tree. Now we need to increase the weight of one edge by 1, so the SPT found by Dijkstra is the same as the MST found by Prims. So what is the difference between the SPT found by Dijkstra's and the SPT found by Prim's? Well, if I scroll up, the big difference is in this BE, right? So we need a way to convince basically Dijkstra's to go the Prim's route. And I was rereading that to figure out if we needed to change Dijkstra's or Prim's, because what's going on in Prim's is, and I can actually go ahead and draw some arrows to make it a little more clear, is we start out by going A to D, then we go D to F, and then we go A to C. Well, even though the exact ordering doesn't matter, we're still doing the same A to C thing going on here, right? But what's different about this is that we are going A to D, but now we're including B to E and then E to F. Instead of having this, what we want to happen is something more along the lines of this. So our question is how we can convince Dijkstra's to say, hey, well, we don't actually want to use BE, use DE so we can get the same resulting tree as you would get when doing a minimum spanning tree. So there's a couple ways to go about this. I think that the most straightforward is you're trying to figure out which one to increase by 1, and you're trying to convince Dijkstra's, right? The issue was that when we got to D, right, we had already seen that we could get to E by a distance of 3 by following AB and then BE. We did not update because the distance from DE, right, using this edge and going around, getting the same distance of 3 was not enough because we need to be less than. So if we increase AB, right, the issue with increasing AB is if I increase this to 2, we're going to the same issue, except this time it'll be E is 4, right? Using BD, DE instead of BE, right? What we basically need is we need this way to be shorter than this to avoid using this in the first place. It's not just enough for them to be equal. So if that's the case, there's only one edge that we can change, that would be BE. We need to increase this to 3, so that way when we get here, we realize E is a distance of 4, and then we come around and we realize, hey, by going this way, we have a distance of 3, and then Dijkstra's will finally be persuaded to go ahead and use the DE edge. So that means that we're going to be going ahead and picking BE as the one to increase by 1.